In this lesson, we will describe some key parts of the transformer and briefly describe the function of each part. First, we will discuss the active parts of the transformer. Active parts are inside the transformer and are the parts that are in direct contact with voltage, current, or magnetic flux. After that, we will cover the inactive parts that you will mostly interact with on the exterior of the transformer. The transformer core provides a magnetic path to channel flux. The use of highly permeable material, usually silicon steel, helps provide a desirable, low-reluctance flux path and to confine lines of flux to the core. The limbs of the core, around which the transformer's windings are wrapped, are constructed of laminated sheets, insulated from each other to reduce eddy currents, which improves efficiency and reduces heat production. A transformer has two different coils on each phase. These are the primary and the secondary windings. The number of turns of each coil determines the magnitude of the change in voltage that will occur when current is applied to one of the windings. The ratio between the primary turns and the secondary turns is the turn ratio. Windings are insulated with a special cellulose paper material to prevent current passage between primary and secondary coils. Individual turns must be electrically insulated from each other as well to ensure that the current travels through every turn of the coil. The steel tank of the transformer holds all of the cooling fluid and is pressurized. It holds all the active parts of the transformer. It is usually bolted to the pad with concrete anchors. There are stiffeners along the walls of the tank that strengthen the tank against the pressure, vacuum, and other forces it is subjected to. The stiffeners allow thinner steel to be used in constructing the tank walls, which reduces the unit's weight while maintaining the same structural integrity as thicker steel. On the side of the tank, you will see a cabinet with lockable doors that provide access to the electrical terminations. The fluid used in a transformer functions as a coolant as well as an insulating medium. It reduces the potential for arcing between windings or grounded conductive parts of the tank. It takes heat away from the core and windings and carries it to the radiator. This fluid is usually mineral oil or ester-based fluid. Most transformers used on solar sites are filled with ester-based FR3 fluid. The low voltage or secondary bushings provide the necessary insulation between the windings' electrical connection and the main tank, which is at earth potential. They seal in the oil and provide an external cable termination to the secondary windings. The insulation is usually porcelain or epoxy resin. Low voltage bushings are typically just bolted lug connections. The high voltage bushings are designed to withstand the medium voltage on the primary side. It is usually easy to distinguish between primary and secondary terminations by their appearance. Primary elbows use large insulating boots to contain the high voltage. There are parking stands where you can place the elbows when they are disconnected from the bushings. These devices are usually installed on the last or the first transformer in a chain. They serve to protect the transformer from very high voltage spikes such as those caused by local lightning strikes, which can momentarily expose the transformer to voltages of 100 kV or more. They link the primary windings to ground through a stack of metal oxide varistor pucks that will create a ground path when excessive voltage is present in order to dissipate that voltage to ground. Windings often have different taps along the coil to allow adjustment of the transformer output voltage by tapping into the coil at different points and effectively varying the overall turns ratio. This is the switch that is used to turn the transformer on or off. It does not de-energize the terminals, but it does open the circuit between the terminals and the coil of the primary side. Some disconnects only have on and off positions, but there are also variations that allow for selective switching of specific secondary circuits. The radiator dissipates heat from the coolant via convective flow. Most PV transformers use entirely passive cooling, where the coolant flows through the radiator via convection, and air moves across the radiator passively, as opposed to either pumping the coolant or blowing the air with fans. The headers of the radiator are flanged directly into the tank and will have a drain plug on the lower header and a vent plug on the upper header.
So in review, the active parts of a transformer include the core and laminations, the windings, the tank and fluid, the bushings, lightning arrestors, tap changer, and the load break disconnect.
The gauges provide important information about the state of the transformer. We usually see a pressure gauge, which displays the pressure of the gas in the headspace above the fluid, either positive or negative, a temperature gauge that displays the oil temperature, and a fluid level gauge. The gas input valve is exactly the same Schrader-type valve you find on a car tire for adding or removing air. In the case of a transformer, inert gas such as nitrogen is used rather than plain atmospheric air, which contains moisture and oxygen. Transformers are equipped with a pressure relief valve to protect the transformer from over or under pressurization. A pressure relief valve, or PRV, is a small valve that has a fixed pressure at which it will open to vent out excess gas. This prevents the tank itself from rupturing at the seams in an overpressure condition. There is a small valve near the bottom of the transformer tank that allows collection of oil samples for chemical analysis. It is a simple gate valve like those found on a garden hose faucet, and it usually has an additional cap over the outlet as a secondary seal. Transformers have small metal placards installed in an accessible location that describe many of the device's properties. On this placard, you can find practically any piece of information about the transformer's ratings, capacity, or configuration. This placard will also display the unit's model and serial number. At a minimum, these labels must contain the nominal system voltage, the arc flash boundary, and at least one of the following: the available incident energy and the corresponding working distance, or the arc flash PPE category found in the PPE category tables, the minimum arc rating of clothing, or the site-specific level of PPE. This label is invaluable in protecting employees who could be exposed to electrical hazards.